What specific problem does the LLM surgery method aim to solve, and why is it important in the context of large language models?
The LLM surgery method aims to solve the problem of efficiently updating large language models, LLMs, by enabling them to unlearn problematic or outdated information, incorporate new knowledge, and maintain performance on standard benchmarks. This is crucial because LLMs often rely on extensive internet-sourced data that may include copyrighted material and personal information, leading to legal and ethical risks. Additionally, LLMs are limited by the temporal scope of their training data, which can result in generating outdated or incorrect information. The proposed framework addresses these challenges without the need for costly retraining, which is computationally expensive and environmentally taxing, as exemplified by the significant GPU hours and carbon dioxide emissions required for pre-training models like LLM-A3. By ensuring LLMs remain current, accurate, and legally compliant, LLM surgery mitigates the risks associated with the widespread use of LLMs in various applications.
How does the proposed LLM surgery framework work? Please illustrate the methodology step by step, including the role of each dataset and the objective function defined.
The proposed LLM surgery framework operates through a systematic methodology involving three key datasets: the unlearn dataset, d-text UNL, the update dataset, d-text UPD, and the retain dataset, d-text RTN. First, it begins with a continually pre-trained model $theta-text pre, which contains knowledge from both the unlearn and retain datasets. The objective function is designed to achieve three main goals: 1. Unlearning specific information from d-text UNL, by applying gradient descent which effectively erases targeted knowledge. 2. Updating the model with new information from d-text UPD through gradient descent, ensuring the integration of this updated knowledge. And 3. Retaining performance on unrelated tasks by minimizing KL divergence between the output distributions of the modified model $theta-text surgery and the original model $theta-text pre, using d-text RTN. This structured approach allows LLM surgery to efficiently modify the model while maintaining its overall performance and reducing computational costs compared to traditional retraining methods.
Can you provide a simple example to demonstrate the inner workings of the LLM surgery framework, detailing how it processes the unlearn, update, and retain datasets?
The LLM surgery framework processes the unlearn, update, and retain datasets through a structured approach. For instance, consider a scenario where the unlearned dataset consists of outdated biographies that the model has memorized. During LLM surgery, the framework applies gradient descent on this unlearned dataset to effectively erase the targeted knowledge from the model. Simultaneously, it utilizes the update dataset, which contains new fictitious biographies, applying gradient descent to integrate this fresh information into the model. Finally, to ensure that the model retains its performance on unrelated tasks, the framework minimizes the KL divergence on the retained dataset, which consists of a large corpus of general knowledge, thus preserving essential knowledge while making the necessary updates. This coordinated process allows the model to unlearn outdated information, incorporate new knowledge, and maintain overall performance.
What are the theoretical or practical advantages of using the LLM surgery approach compared to traditional methods of updating large language models?
The LLM surgery approach offers significant theoretical and practical advantages over traditional methods of updating large language models, LLMs. Firstly, it employs a novel objective function that integrates unlearning, updating, and retention in a single framework, allowing for efficient modifications without the need for costly annotations, which is a common requirement in traditional fine-tuning methods. Secondly, LLM surgery leverages existing knowledge embedded in the model, enabling targeted unlearning and updating while maintaining performance on unrelated tasks, thus avoiding the high computational costs associated with full retraining from scratch. Empirically, LLM surgery demonstrates a 35x reduction in GPU hours compared to naive approaches, highlighting its efficiency, especially as the size of the retained dataset increases. Additionally, the framework effectively addresses legal and ethical concerns, such as compliance with the Right to be Forgotten Act, by directly modifying model weights rather than relying on in-context learning or fine-tuning alternatives. Overall, LLM Surgery unifies unlearning and updating processes, making it a scalable and effective solution for managing LLM knowledge.
How is the effectiveness of the LLM Surgery method validated? What experimental design and metrics were employed, and what do they signify?
The effectiveness of the LLM Surgery method is validated through empirical experiments using the Llama 2-7B model, where three distinct datasets, unlearn, update, and retain, are utilized to assess the model's performance before and after applying LLM Surgery. The experimental design includes generating multiple-choice question-answer (MCQA) examples based on these datasets, with accuracy as the primary evaluation metric. Specifically, the results indicate a 19% reduction in accuracy on the unlearn benchmark, confirming successful unlearning of targeted information, while a 20% improvement in accuracy on the update benchmark demonstrates the model's ability to incorporate new knowledge. Additionally, the model maintains comparable performance on the retain benchmark, indicating that LLM Surgery does not degrade the model's knowledge of unrelated tasks. This comprehensive evaluation signifies that LLM Surgery effectively balances unlearning, updating, and retention of essential knowledge, showcasing its potential for practical applications in large language models.
What specific empirical results were achieved with LLM Surgery, and how do these results support the claims made about its effectiveness?
The empirical results achieved with LLM Surgery demonstrate its effectiveness in three key areas: unlearning, updating, and retention. Specifically, the modified model bold symbol theta-text surgery exhibited a 19% reduction in accuracy on the unlearn benchmark compared to the original model bold symbol theta-text confirming successful unlearning of targeted information. Additionally, bold symbol theta-text surgery showed a 20% improvement in accuracy on the update benchmark, indicating its capability to incorporate new knowledge effectively. Importantly, performance on the retain benchmark remained stable, suggesting that LLM Surgery does not degrade the model's knowledge of unrelated tasks. These results collectively validate the claims that LLM Surgery can efficiently modify LLM behavior while maintaining overall performance.